This is problem 6-24. It's on page 279. Determine the force in each member of the truss and state if the members are in tension or compression. Set the external load P to 4 kilonewtons. Now in this section of the chapter, we are considering only the method of joints, not the method of sections. So let's sketch the truss that we're considering today, that we have under consideration. And I don't like that drawing. Let me try again. So this is point F, point E. There's another member across this way. Here's point B, point A. Load P is applied here, 4 kilonewtons. There is a pin at B and a roller at joint C, as well as another load P at point D equal to 4 kilonewtons. Now the free body diagram of this is pretty trivial. Let me just draw the reactions here. It's pretty obvious Bx is 0, right? There are no external loads causing any force in the horizontal direction. And since the whole thing is symmetrical, it's also pretty obvious that we must have 4 kilonewton reactions at B and C in the vertical direction. If you don't know how that's done, we'll just some moments say about point B to get rid of this reaction, and you'll find that the reaction at C is 4 kilonewtons, then some forces in the y direction. And you'll find that the other reaction is also 4 kilonewtons. So that's pretty straightforward. But that's not really the point of this part of the chapter. The point is to solve for forces in all the members using the method of sections. Now to keep everything straight, I think I will make a table of all the members, and I'll put them in the order that I ended up solving them in. AF, FE, let's see, surely I have AB in there somewhere. There it is, yeah. So I solved for AF and then AB, and then I solved for FE. After that, I solved for FB. Let's see. AF, AB, FE, FB. Probably move to point B next. Yep, so that would involve BEBC. And then we can either go to E or C. I chose to go to C. So point C, I then got BC. Oh, I've already written it here. BC in order to get CD. There we go. And then CE. And finally, ED, although it barely fits. There we go. So we'll need to know the force in each member and tension versus compression. Hopefully I can keep all of this straight. Guess we'll do something like that. There we go. Of course, we're in English or metric units, so the force will be in kilonewtons because that's what's given. And tension or compression obviously has nothing to do with English or metric units at all. So let's start off by taking point A and writing down the free body diagram for point A, assuming that all of the loads from members are tensile loads. Now I've put the external load P in here as well. And what we'll do, you notice that the vertical component of P is counterbalanced by the vertical, well, all of P is counterbalanced by the vertical component of AF. So what we will do is begin by summing forces in the vertical direction. In that case, we have negative P plus AFY. But AFY, I didn't draw the geometry here, or the dimensions, but basically the truss is 3 meters, 3 meters, 3 meters, 3 meters. So the angles are all 45-degree angles. So if we want the vertical component of AF, we will just divide by the square root of 2, and this sum must come to 0. So AF must be root 2 times P. So if we know that P is 4 kilonewtons, now we know that AF is root 2 times 4 kilonewtons. And I'll just write it that way, 4 times root 2. And it came out positive, therefore my assumption of tension was correct. If we sum forces in the horizontal direction, we'd have AB plus AFX equals 0, because notice both of those have positive components in the x direction. And so solving for AF, x I guess, it's negative AB. So what I can tell from the very beginning is that I've chosen the wrong direction for AF. AF is in fact in, oh no, wait a second. We've got, no, I've got it backwards, I'm sorry. We're solving for AB, let's try that. AB equals negative AFX. I've assumed the wrong direction for AB. AB is in fact compression, not tensile. So since I know AF, I will write negative AF, and again, I need the horizontal component, so it's just divided by root 2. So AB will simply be 4 kilonewtons, but it is a compressive load. In other words, this would end up being, negative 4 kilonewtons, because AF is root 2 times 4. So the root 2's cancel. Okay. So now we know the force in member AF and AB. And let's carry on. Where should we go to? Well, I chose to go to F next. Could you go to B? Problem with B, while you know one of the loads here, you know an external load, there are 1, 2, 3 other truss members. So I would not go to B. I don't think it would work out well. Rather, I would go to F because there are fewer unknowns there. And in fact, with F, we will be able to solve for one of those problematic unknowns that would plague a solution to B. Okay, so notice F is an easy one because we already know AF, and so there are only 2 unknowns, FE and FB. Now it should be fairly apparent that the horizontal component of AF and the vertical component of AF are equal to FE and FB respectively, but let's write it out. Sum of forces in the horizontal direction, negative AFX plus FE equals 0. And so FE is just, positive AF over root 2. AF is 4 times root 2, so FE comes out to 4 kilonewtons. And since it's a positive thing, it must be in tension. Now FB we'll get by summing forces in the vertical direction. And so that would be what? Negative FB minus AFY equals 0. And here, FB then must be the negative of AFY, but AFY is just AF over root 2 again. And so here we get 4 kilonewtons, but this is a compressive load. So FB is a compressive load rather than a tensile load. So now we solve point F, and notice what that gave us is one of the members that would have plagued a solution to B. Right now we know the load in member FE and FB. We also know the load in AB. So a free body diagram of point B will have 2 unknowns, BE and BC. Let's take care of that one next. So here's point B. Point B has load AB, reaction BY, BC, BE, and FB. Notice I'm always drawing these as tensile loads. Now, of course, BY is not coming from another member. It's a reaction from the ground, and so, or from a pin connected to the ground. So I just draw it in the direction that I know it actually acts, okay? So if I sum forces in the y direction, why would I do that? Well, I know AB, I know FB. So if I sum forces in the vertical direction, I can calculate BE. BC will not appear in the equation, whereas both BE and BC will appear in the equation for the horizontal sum of forces. So summing forces in the y direction, we've got By plus Fb plus Be in the y direction equals 0. Those are all the forces that have y components for point B. So rearranging this just a bit, we will get Bey, which is, well, it contains the unknown, equals negative By minus Fb. And Bey is the same thing as Be over root 2. Why? Because Be is at a 45-degree angle also. Remember, the width here is 3 meters, the height is 3 meters, that makes Be at a 45-degree angle. And so its vertical and horizontal components are just its hypotenuse divided by the square root of 2. So basically Be will be calculated as root 2 times, or negative root 2 times, By plus Fb. So negative root 2. By we know is 4 kilonewtons. Fb we know is, well, now be careful here. Fb is 4 kilonewtons in compression. Notice I drew it in tension again, being consistent. And so since I see it's compressive, I know that Fb is actually negative 4. And so these two actually cancel. So that means Be comes out to nothing. It's 0. There is no force in member Be. Now the reason that happened is because if you think about Be not being there, it seems like it would be a problem, right? Because it seems like that, you know, this square here, which is actually a 4-bar mechanism now that I don't have that stabilizing member, it could actually roll. But the forces are all completely balanced, and so there is no necessary force in Be for this particular loading scenario. Other loading scenarios would require member Be to take some load, but not this particular one. So this is a fairly straightforward loading application. So we sum forces in the vertical direction and found that Be is 0. How about summing forces in the horizontal direction? Well, sum forces in the horizontal direction, what do we have? Negative AB, that takes care of that one, plus BC. And Be doesn't contribute anything, neither does By or Fb. So this comes out to 0. Basically what this says is AB equals BC. Now let's see, AB is known, now BC is known, it's the same thing. Now notice that it's positive, right? Or, well, AB is exactly equal to BC. I've assumed that AB is tensile and BC is tensile, but in fact AB is compressive, therefore BC is compressive. And Be being compressive or tensile doesn't make any sense. So BC is negative 4 kilonewtons. BC is also in compression. All right, so we're moving along nicely. We've only got 3 more members to solve. If we take a free body diagram of pin C, or joint C, then we'd have 4 kilonewtons. Well, I guess I could write it this way. We'd have Cy, which is 4 kilonewtons. We'd have BC, notice I'm drawing it tensile, even though I know it's compressive, CD, and CE. And now if we sum forces in the horizontal direction, we would find that BC and CD are equal to one another. So we can just write that down. CD is the same thing as BC, 4 kilonewtons in compression. Notice I drew them both tensile, but in fact BC is compression, therefore CD is also compression. So I guess I should say it this way, BC equals CD. That's pretty obvious from the free body diagram. If we sum forces in the vertical direction, well, Cy we know acts upward, therefore CE has to actually act downward. And so CE will be the negative of CY. So CE is not tensile either, right? Because think about it. CY acts upward, it's just a positive 4 kilonewtons. So CE is compressive at negative 4 kilonewtons. Okay? So that takes care of CE and CD. Finally, we can move on to either point E or point D in order to solve for the force in ED. I chose to go to point E and use point D as a check. So point E has FE here, ED here, and CE acting downward. However, it also has BE. Now, for this particular loading configuration, as I said, BE is 0. Okay. So if we sum forces in the horizontal direction, we'll get negative FE plus EDX. Right? And that's it. The sum is 0 because remember, BE has no force in it. And so EDX, how would we write that? Well, again, it's a 45-degree angle, so divide by root 2 to get the horizontal component. And so ED, let's try D, not B, ED equals root 2 times FE. Okay? So let's see, if we look at FE, FE is 4. ED is positive, just as FE is. So ED is a positive, let's see, wait a second. Oh no, it's 4 times root 2, there we go. So 4 root 2 in tension. Now, what you should notice at this point is that since this is symmetrical, our loads should come out symmetrical as well. For example, FB and EC should be the same. FE and BC, yep, both are 4. I'm sorry, not FE, FB. There we go. I was going to say one's tension, one's compression. That doesn't make sense. Yeah, FB and EC are the same. They are both compressive loads at 4 kilonewtons. AF-ED should be the same. Now let's see, there's AF-ED. Sure enough, 4 root 2 tension. That makes sense. How about ABCD? Well, AB for compression, CD for compression. Yep, that makes sense. And what else? Well, FE, there's nothing for it to be symmetrical with, as well as BC. So FE and, let's see, FE and BC. Just have to check those off and make sure that everything else works. But then BE was 0. So what else can we do to check to make sure all of this is correct? Well, we could take a free body diagram of point D. So point D has ED acting this way, CD acting this way, and P acting downward. If we sum forces in the vertical direction, let's see, what do we get? We get EDY, the vertical component, minus P equals 0. Well, EDY is ED over root 2. And so if we plug in the value of ED, what is it? It's 4 root 2. P is 4, and sure enough, yes, that is 0. So that works. If we sum forces in the horizontal direction, what do we have? Well, let's see. Negative EDX minus CD equals 0. It's a question that we're trying to verify. So this is the same thing as ED over root 2. And so let's see. ED is a tensile load for root 2. Let's see, root 2 minus CD. CD is a compressive load, so it is a negative 4. And let's see, so root 2's cancel. We have positive 4 minus 4 equals 0. That checks out. Okay. Now there was one more check I could have performed on point E. I missed it. I won't bother with it now, but you could have summed forces in the vertical direction for point E and would have also come out appropriately. So that's it. We've solved for all of the forces in all the members, and we know whether each has tension or compression in it.